Perth Linux Users Group, talking Linux and open source.
Thank you very much, Chloe. With the conversation, with the confusion about jobs, I'd like to make clear that this is Jeremy, the free software hacker, talking here, not Jeremy, the canonical employee. So this is all personal time stuff. I can kind of talk about some of the public statements we've made about it. Of course, I can't talk about anything private, but there's not a lot of private stuff. So, but happy to answer any questions. But don't take this as Canonical's, the company's view of how things are going. A lot of technical content. If there's anything at all you want to stop me and ask me about, please do. It can get pretty dry, and if I kind of start going off on a tangent, it'd be much better if you kind of pulled me back online. So that'd be great. So yes, my name is Jeremy Kerr. I do have Canonical. I've been working on UEFI, Secure Boot and Linux for maybe kind of 9 months in a sort of serious aspect, and just want to kind of tell you guys about what's happening, what it means for Linux, why we're doing this sort of stuff, and I guess if you want to get into it, how you can. So firstly, I guess a bit of background is in order. We're used to, I guess the PC BIOS traditionally, and that's the kind of not so great interface we see when we boot up the machine. Has a lot of options. This one's got a robust graphics booster. I have no idea what that is, but this kind of thing, it's responsible for the low-level machine in it. So bringing up the CPUs, bringing up the memory, making sure everything's clocked right, getting some of the peripherals going. Not all of them, because the rest of that's up to the operating system, but doing enough so we can start booting our bootloader, which then boots the kernel and then boots the rest of everything else. So,
does that one come with Men in Black?
I believe so. Yeah. MIB2 automatically. Yes. So basically, to sort of bring you through some of the internals of what happens in BIOS and its legacy backgrounds, let's take you through a story about how we read something from a disk using the PC BIOS interface. Now, PC BIOS is run in 16-bit mode. Everything's real addresses, so no memory protection is running at this stage. And most of the entry points into the BIOS are done through interrupt calls. So you set up your registers and you call one of the interrupts, and the BIOS then handles that interrupt, does what you ask it to do, and then returns some data. So this is how we do a read in the PC BIOS world. Read a block from disk. We set up some registers. AH2. We set the register AH to 2. We set AL to be the number of sectors we want to read. CH, CL, DH, DL, parameters of the reads, and then we supply a buffer address that we want our data read into. So we then set up the registers, call interrupt 13, BIOS goes and does something, and hopefully we get our block of data back in the buffer we just provided. Now, a few caveats here. Firstly, I think the heads, no, the head's fine. The sector goes between 0 and 63 because we've got 6 bits there. But in actual fact, the sector number starts from 1. So there's a bit of a gotcha there. Also, some BIOSes have a problem when reading more than 127 sectors at a time. So you don't want your number in AL to be too high, otherwise the BIOS would tend to do something crazy on some machines. Other machines it works fine. So a bit of a legacy thing there. Also, I think the head number, if you go above 255, if you try and read 255 or head number 255, often that doesn't work because Windows had a bug ages ago where it didn't support machines with 256 heads. So we carried that over. We don't read head number 256 anymore. Also, if you call this and your disks aren't spinning up yet, it might return an error. So we generally call this 3 times in a row if we see a failure, just to make sure that the error was actually a non-recoverable error. So there's a lot of cruft in this interface now. There's a lot of things we don't want to do. And the major problem here is we have 3 registers set for our cylinder, head, and sector. We don't actually use those anymore for a start. If you read off cylinder 5, head 3, sector 4, often that's translated to a completely different part of the disk. Disks these days have their own translation layers. They generally don't necessarily read from that same sector you're going to ask for. But the real problem is there. We have 3 16-bit registers to hold those parameters, which gives us 24 bits. 3 anyway, we have about 8 gigabytes of address space here, which means if our disk is bigger than 8 gigabytes, we can't address it by this read. So when we were kind of coming to that 8 gigabyte limit, when disks were getting to that size, we introduced a new, when I say we, I say not me, I wasn't around in this time, but they introduced a new interface to the BIOS called read extended. Now, similar sort of interface we call interrupt 13. We set up our registers a bit differently. We give it a drive index and an address in memory of a packet. Now, this packet describes the operation we want to do because we can't fit our operation in the registers anymore. We have to move it out to memory, and in the registers we put a little pointer to that packet. So the packet, we have a few fields, the size of the packet, just to make sure both the BIOS and the caller are talking about the same thing. The next field is reserved. This 2-byte value gives the number of blocks to transfer. Again, we're limited by some BIOSes. Some don't let us read above 127, so there's still some carryover happening here. But this time, rather than three registers for the value, we have a 32-bit address. We have a 32-bit block number. So we can read 32 bits worth of blocks, usually in 512-byte sectors. So that gives us about 2 terabytes of addressing here, which is better. But now we're kind of seeing disks becoming more than 2 terabytes, which means this interface no longer works. So we extended the read extended, and now we have an 8-byte field in this packet. Now we can tell this packet from the other packet because that one had a 10 and this has an 18 hex. So if we want to read above that point, we use the 18 hex value. We put our 64-bit sector number here, and that gives us more than we'll ever need in terms of disk. Right? Yeah. I hope. Shut up. So we have 64 bits of address. That should be enough for anyone, right? So we can read off anything now, right, with this new interface? Well, not really. At the beginning of disks in the BIOS world, we have a master boot record. And that describes where your partitions are. You can have up to 4 of these. Or you can have extended, but we won't worry about it. You have this master boot record with partition table entries. And this is the format of the partition table entries in the master boot record. Don't worry about these things. We don't need them now. But the main thing is we have an index of the first block and the number of blocks in the partition. Now, these are 32-bit values. So that brings us back down to 2 terabytes of maximum address space. We can't have any partitions that start beyond 2 terabytes, and they can't be more than 2 terabytes in size. So this is the kind of the other limitation here. We're stuck with disks 2 terabytes or less using this interface. So there's no way we can write a program against BIOS that reliably addresses anything beyond 2 terabytes in a disk. Now, rather than writing read extended with a different master boot record, we kind of need to think about this again, and the answer to that has been proposed as being UEFI. Now that's UEFI stands for Unified Extensible Firmware Interface, and it's actually a specification. We have a document that specifies how UEFI is structured, which defines the interface that BIOS programs are going to talk to the BIOS, and how different bits of the software interact with your BIOS. When I say BIOS, it's really firmware. When I say BIOS, it can mean generally means the legacy PC BIOS world. Firmware, UEFI, the new stuff. So there's a group called UEFI.org, made up of several companies, HP, AMD, Intel. Intel's the main player. Canonical and Red Hat are also members of UEFI. So we have some participation in their working groups, and just to making sure that Linux is sort of a relevant player in the UEFI world. Now, rather than a bit of a, I guess, technical background again, I won't go through the whole thing, but talk about some of the internals of how UEFI works. And there's really 3 components: services, protocols, and handles in UEFI. Services are kind of the global operations in the system. Things like reset system, that's pretty global. That's pretty much as global as you can get. You call this function and the system will reset, either like a cold reset, warm reset, or we can shut down. Now you'll notice I've given you a C prototype here. Most of UEFI is provided in terms of, or most of the interface is defined in terms of C. So rather than calling interrupts with our registers set in a certain pattern or our memory buffer somewhere else, We just use the C interface. Now, you can write it with any language you like, but as long as you pass things in the C calling convention, then that's fine. So this here is our reset system service. And we also have a get variable service. So this allows any software that's talking to BIOS to get the value of a variable out of UEFI. There are all sorts of variables. One, for example, is the order in which you boot from devices. So you can say boot the CD first, boot the hard drive second, and using this this get variable call, you can ask the BIOS to tell you how it's booting. It's also similarly a set variable call. We can use this to set variables, and there's all sorts of variables. There's variables that are just used during the boot time, variables that UEFI has no idea about. You can just call your own variable if you like. There's variables that are non-volatile, so they'll stay persistent between boots. So there's all sorts of different variables used by UEFI, and it allows, I guess, some sort of interaction and storage between programs that are talking UEFI. Now, another component of UEFI is handles. Now, I've been pretty vague here, saying a reference to something. A handle may be a reference to a device in the system, like a disk or a network card, or it could be a reference to something like the IPv4 stack on your network card, or the currently running image. Or handles themselves aren't. It's somewhat abstract and represent something system, but not so interesting on their own. What is interesting is protocols. Now, protocols define the operations you can do on something in a UEFI system. So you might have a disk handle, and a protocol says how you can interact with that disk. So you can read or write, or you can format or whatnot. Or you can, let's say you have a network device. That might have a protocol attached to say send packet or receive packet. So these protocols define standard ways that you can interact with different bits of your UEFI system. So for example, let's talk about our reading from disk example 4. This is the way you read or write, or you interact with the disk device. You get a handle, and you can operate. You can, if it implements this protocol, you know you can do these things to it. So you can reset it, you can read blocks from it, you can write blocks from it, or you can flush the blocks in that system. So again, to use our reading from disk example, this is the read blocks method of that EFI block IO protocol. We give it a logical block address. So again, that should be 64 bits, enough for anyone, right? I think it's 64. Anyway, it's an LBA. And a buffer of where to read into, and it reads that. We don't have to call it 3 times. We don't have to worry about the CHS mapping. We don't have to worry about restrictions on sizes where Phoenix BIOS didn't do this, and Award BIOS didn't do this, and some other BIOS. We just have a plain C function we can use to call here. And there's a whole bunch of these different protocols to do different things in the system. And rather than trying to find your disk device and saying, okay, let's try and read from that disk, you can basically discover all of the handles in your system, all of the devices that implement a certain protocol. So rather than going, okay, I know disk devices I can read from, but there could be any other type of device that supports block I/O, for example, an SD card. So you can say, get me all of the devices in the system that implement this disk I/O or this block I/O protocol, and then you can just start doing block I/O to them. So that's the kind of the extensible part of UEFI, in that you just need to, I want to do this, tell me what I can do it on, and then you can just start doing it. So you can boot from an SD, or theoretically you could boot from an SD card or a disk exactly the same way, without having to worry about how it's actually implemented on the hardware side, which is pretty useful for a bootloader. You don't want your bootloader to get too complex. You don't want to have to start doing device discovery too much in your bootloader. You boot your bootloader just to use the services it has to boot to the next stage of the system, which is your operating system kernel. Now, speaking of keeping bootloaders nice and small, rather than reading a block from your device and then trying to decode the file system type on that device and then decoding how the file system works and has laid out its data, you could just use something like the EFI load file protocol instead. Now, this is another protocol. It might be implemented by some devices in your system. It might be implemented by a number of devices in your system. And it says anything that implements this protocol has a load file function. And that load file function must look like this. So you give it a file path, don't run a boot policy, and a buffer, and it reads that file into your buffer, and you're done. So that potentially removes a lot of code from your bootloader, because you're just telling the firmware do the block I/O, to decode the file system, to do the path iteration to get to the right place in the file system, read the data out, and just put it in your buffer. So with these sorts of interfaces, we can get our bootloaders very small and not have to worry about kind of differences between systems, differences between file systems that are present, and that sort of thing. Any questions so far about protocols? That's yes.
Which file systems? I think that's obviously going to be specific to the UEFI kernel.
That's right. So it's extensible. So you could potentially write your own file system and have that loaded at boot time. You could drop a file in and have that run as an UEFI application, which provides an XFS file system, for example. So that's the extensible part. You register your own protocol and say, okay, I support these devices. I can do XFS on blah, and blah. And then you just say, okay, load file, and then you implement all the XFSE bits, and you return the data. So I think we'll probably find that maybe VFAT is the only one supported. I don't know. There might be some demand for NTFS. There always demand for EXE2, but it's really up to the system implementer to what bits they put into their BIOS or their firmware. And so I think I'll get to sort of how we get around that in a bit. But in theory, it could support anything. So anything that you want to write code for, you can do. Yes.
What is it that you're actually giving us? Are they the specifications, or are they the?
Yeah. So this is I've taken this directly from the UEFI specification, and this says if you have a device that supports that protocol, it has to have a function that does exactly that. So this isn't me writing code. This is from the specification that says. Yeah.
It's been finalised now, because I know that there were all these different drafts, but I guess it's final now.
I mean, it undergoes a lot of revisions. We're at version 2.3.1 at the moment. There's always work happening on it, but it's pretty solid. The protocol interfaces aren't changing. There's more refinement on making sure we have the right error codes and that sort of thing. So if you're calling this, you're probably going to get it for any UEFI system. Yeah. So I guess that's probably enough about the internals of EFI. Things that matter to probably to us most. So in reference to the what file systems we can be using, most EFI systems will have a what's called an EFI system partition, and that's just a VFAT partition. Generally, doesn't have to be at the beginning of the disk like old BIOS does. It can be anywhere you like. It's just given a certain partition type. Generally loaded on my system here. It's the first partition. That's only by coincidence. It's generally mounted onto /boot/EFI, and in this case, I have one file in mind, which is the grub executable, and that's the type of the file. It's an executable PECOF binary. It's not. I guess that's a bit of a misnomer. It's not necessarily from MS Windows. You probably can't run it in MS Windows, but we have the tools on Linux to build these things, and grub itself is quite easily compilable into one of these EFI binaries. You notice here we're using a certain path, EFI/Ubuntu. That's a well-defined path. The name Ubuntu is reserved in the EFI specification. There's the various companies have registered their own paths as sort of proper locations, but it doesn't necessarily have to be that same. And the file name grub.exe4 isn't a standard path. That could be anything. And the way we tell grub that this is the thing we want it to boot, the way we tell EFI this is the thing we want it to boot when it comes up, is through the UEFI boot manager. And this is basically the bit of UEFI that's responsible for passing control off to the next thing, usually your bootloader. And there's a command in Linux called EFI boot manager, EFI boot manager, and it basically does get variable calls against UEFI and queries how the boot is supposed to work. There's a variable called boot order, and that says boot 0, then boot 1, then boot 3, or try 0. If that doesn't work, try 1. If that doesn't work, try 3. My option 0 has a name of Ubuntu, and it's on my hard drive in that location there. Now that's from back here. That's that same location. That's how EFI knows I want to, when it starts up, try booting that grub file first. If that doesn't work, try legacy mode on the hard drive. Otherwise, try booting off the network card. So, yes.
I noticed that it's using something vaguely reminiscent of grub to identify a partition there. The HD parenthesis 1 comma dot dot dot. What does the dot 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 mean?
That means that was too long to fit on the slide, so I took it all out and replaced it with dot dot dot.
Oh, is that a GUID there, is it?
Yeah. So it's a GUID. It's
Okay.
about this long. So
Yep, and that identifies the partition. Is 1 the hard drive identifier? How does it know which drive 1 is? And does that change if you install new drives or move the endpoint?
I think it's probably the first partition of that GUID. I think.
Well, no,
Yeah.
partitions have GUIDs, disks don't.
Well, the file systems have GUIDs.
Yeah, well, if it's got a file system on it, the partition will, and that's why I'm imagining that the 1 belongs to the hard drive and the dot dot
I'm
dot
not
is
entirely sure.
the particular file system.
Yeah.
Anyway.
But it's a string representation of a device path object. So, opaque blob, it just deals with that and it works. So, but yeah, good point. We use GUIDs a lot in UEFI to identify bits of the system or protocols or handles or whatnot. So, I kind of just deal with it as an opaque blob and that's it. But yeah, good point.
Existing chips on a board, on a main board, or have you got to have custom chips to do this?
To run EFI?
Yeah.
You probably find any computer you've bought in the last 2 years or so already has an EFI BIOS.
Oh, okay.
They often operate in legacy mode, so legacy emulation mode. So you see here, if it doesn't find this boot option, it'll try and boot this guy in legacy style, and they can often do that. So as time goes on, there's a plan to sort of phase out those legacy BIOS interfaces. So we'll have to start using
So
EFI.
is UEFI the one that Microsoft wants to put into Windows?
Yes. Yep.
With the encryption thing?
I've got
We'll get to that.
a big section of that. That's why I'm here. That's right. That's why you're going to yell at me later.
Sorry, following question from that.
Yep.
Is it possible to flash an older BIOS, say, on a decent motherboard brand like Gigabyte or Asus or something, with a UEFI firmware image, even if it didn't ship with that in the factory?
It's really up to your machine vendor. There's a lot of low-level code that may or may not. I mean, there's a lot of hardware initialization that needs to be done, which may not be present in BIOS. So you'd probably need to, like any other BIOS upgrade, you'd probably need to have that provided by a motherboard vendor or whatnot. Are you interested in a playing with UEFI kind of perspective, or no? Okay. So there's, if anyone else is, so Intel, who are major contributors to UEFI, have written a reference implementation of UEFI, and that's open source. So you can grab the code, build it up, and boot it in QEMU. So actually, let's do that now.
Live demo.
That's right. Cool. So this is Intel's latest checkout of Intel's UEFI binary or UEFI source code, built up and booted into QEMU, and in this case it couldn't find anything, so it dropped down to the UEFI shell because I haven't given it any devices. But that's it. So that's UEFI binary. We can do various things in the shell here. I'll just reset it. Hit the magic key to get into the configuration, and we've got this is just the sort of normal BIOS you'd see on a machine that uses this. So it's all open source. You can grab it, compile it, play around with it. I actually use this quite a bit in kernel development because I can see exactly what the BIOS is doing and what it expects of the kernel to do and that sort of thing. So that's been really handy for me. Cool. That went much better than expected.
Yeah, I just had a bit of a quick question. A bit of background, I do sort of imaging for Windows as part of my job as well. Is there any sort of automated way that UEFI goes looking for the boot image? So I'm just thinking when we're mass imaging machines, how how does it find
Mm.
the boot image?
Yeah, that's an interesting problem. I don't include yeah. So here we go. So if you boot anything with the removable media, because it's not you don't expect to have your UEFI set up or configured to boot that, then it looks in some standard locations, or it looks in a standard location, and that's /EFI/boot/ so boot something.EFI. And on x86-64 machines, it's x64. Now, I have a feeling that this is also implemented for non-removable media for pretty much exactly that situation, as a bit of a fallback for situations where you haven't configured the boot manager correctly. So, and that really depends on the firmware that you're running on that machine. So, but yeah, there is a standard location for not quite sure yet.
I'm sure I could build something to take advantage of that.
Yeah, definitely. But yeah, I mean, you could, in theory, just like plug a USB stick in. If it's in that place, so it's in that location, then it would start booting that and go. So the Ubuntu CDs or the USB images all have their bootloader at that location, and that's how you stick it in an EFI machine and it boots and it starts installing or live CD or whatnot. So that's to address that problem. Cool. A bit of sort of background on how someone writes their programs against this UEFI API, and the classic way of doing that, right, is Hello World. So we have a UEFI entry point, EFI main. All the EFI applications are given a reference to the image themselves, the image that itself that's running, and a pointer to the UEFI system table. And that contains all sorts of data about the system, like how to locate the rest of the functions, how to get the ACPI tables, all sorts of configuration and runtime parts of the system. Most of the, for example, here we're using the system table to find out the console output device, and we're printing the string "Hello World" on that console output device. And then, in this case, we're actually returning. If you're a bootloader, you generally don't return because you've started executing something else. But you can write a simple application that does something little, prints out a string, or maybe configures your new boot path and sets the variables to set up your new install, that sort of thing, and then returns. So, like any sort of application, that's how we do a Hello World. And in this case, I'm using EFI lib. That's it's a GNU sort of C runtime environment for EFI. It's in the GNU EFI package, probably on most distros. That allows you to write these EFI programs without too much sort of low-level messing around. Cool. One of the final things is once your bootloader is started and wants to free up the memory and the resources used by EFI, it can sort of shut down all the boot services. So things like its network stack, you probably don't need that because you've got an operating system running. All of its file systems, that you can sort of clean it up and go into runtime or EFI runtime mode, where you've got a few things left around, so you can still set and get variables, but most of the functionality of EFI is gone. So in order to transition from boot services to runtime services, we call exit boot services. And that tells EFI, look, we've finished, we're running now in full system mode. We don't need to use EFI to access the disk. We don't need to use EFI to do IPv4 on the network cards. So that kind of delineates time to boot time to kind of runtime. And that's how we do that transition. So the one of the features of UEFI is secure boot, and there's a bit of technical background, a bit of sort of public key cryptography here. So I hope it's not too dry and boring, but let me know if there's any bits that aren't clear. I've simplified it a bit. If you need details about things, I'm very happy to provide them if I know it. So secure boot is a method for EFI systems to verify the thing that they're booting, making sure it's not malware, making sure you haven't got a compromised binary, or you're not booting something you don't want to boot, basically. And I guess the justification here is that we're seeing operating systems becoming a lot more secure now. We're seeing driver signing for Windows that to prevent malicious code being loaded at the kernel level. We're doing a lot of work in Linux on different access policies, SE Linux, all sorts of things to really harden systems against rootkits and bootkits and that sort of thing. Now, we haven't got the same sort of security considerations up until now in BIOS. So generally, if you have if your boot sector of your disk is corrupted, or if some malware writes to that, it's game over. You're running whatever code has been put there. So secure boot is an attempt to address that in terms of making sure that you're running the stuff you want to run. Now here's the description. So I'm a software author. I'll pretend to be one now. I have two things. I have an image I've just built. I've got that Hello World application. I've built it into an UEFI image. I've also got an RSA key pair, so public-private key, standard stuff. Nothing exciting there. But the main thing is that private. I'm the only one who has the copy of that private key. That public one can go anywhere, being public and all. So I get my compiled Hello World binary, my UEFI image here. I then create a hash of it. Again, standard SHA-256 algorithm. I then encrypt that hash. Again, bit of a simplification here, but I encrypt that hash with my private key. So in theory, I'm the only person who could have generated that purple blob at the end, because I'm the only one who has a copy of that private key. I then take that signature and put it back into the UEFI image. I can do this without changing what the algorithm used to generate the signature, but at the end of the day, I have my key pair and my UEFI image. Now, if I give you my public key, you can take this image and say, yes, this came from Jeremy. Or you can, there's nothing special here. This is done all the time. This is, it's done when you PGP sign an email. It's done when you get it. It's all a Debian package, exactly. So nothing special here at all. The formats, some of them are specific to UEFI, the UEFI sort of boot protocol, but nothing special. So what we can do is put my public key into your firmware. So let's say you want to run my software for some reason. You take a copy of you trust me, you take a copy of my public key, put it into your UEFI firmware. Now I have no role to play here anymore. Using that firmware, you can use my public key to verify that this image indeed came from me, or at least came from the owner of the person with that private key. So that's pretty much the essence of secure boot. You have a public key somewhere in your firmware and use it to verify UEFI images that you boot. Now, you actually have multiple public keys in there. There's a whole database of, actually multiple databases, but you're not restricted to just having one public key in there. You could trust me. You could also trust James. You could also trust James as well. So you can collect these public keys depending on the people you trust to run software on your computer. So like I said, we have this signature database of keys that you trust, and we use this. This is the main thing that's used during the image verification process. We also have a forbidden signature database. So we can use this to revoke. Let's say I wrote a Hello World binary or Hello World UEFI application, compiled it to binary, and there was actually a buffer overflow in it. And now some malware is using that to exploit systems. You can then put an entry into your firmware saying, okay, I no longer trust either that binary or anything signed with that key. You can put different things into that data forbidden signature database, but the main thing is you use this to revoke access from known bad bits of software. Now, we don't have complete we don't allow free access to these two variables. If they were, malware could just insert its own key into that and then boot. So we need to protect these somehow from malicious alteration. So we have what's called another key database called the KEK, or key exchange keys. Now, if a key is in, this gets a bit complicated. So in order to update these two, the DB and DBX, you put a new key into them or put a new revoked key into them. Now, you can't just put any key in, so you have to sign your update to those databases with one of the key exchange keys. And then that will then allow you to insert that key into to do a set variable on either of these two. So you have to do like a set variable with the thing you want to put in there plus a bit of an authentication descriptor which sort of verifies that the thing you're trying to put in is actually from another trusted source. Is there any questions about that? Yes.
Is this all at the level of your machine?
Yes.
You actually.
Yep. So this doesn't, but if it had UEFI firmware, it would have a DB, a DBX, a KEC, and another one. But yeah, this is all on one machine, and it's not sort of shared or anything like that. It's just purely specific to one machine. So as I said, we have another key here. Now it's called the platform key. Now the UEFI spec defines that as, I think it's the key belonging to the platform owner, but it doesn't define what the platform owner is. So some people read that as the person who owns the laptop. So if I have this laptop, I should have the PK in there. Some people read it as, since the laptop came from Lenovo, it should be Lenovo's key in PK. But it's not used a lot. It's kind of just the root of trust in there. The only thing that does protect is that if we want to put an entry into KEC, it has to be signed by PK. So we kind of have these three levels of trust. It gets a bit complex, but the main thing about the PK is that if the PK is absent, now we kind of have, I guess, a bootstrapping problem here. If updates to these two have to be signed by something in here, and the updates from this one have to be signed in here, how do we get the first key in there? And that's done by what's called setup mode. So if the PK is absent from a system, it's said to be in setup mode. In setup mode, you can put any key in anything. So that allows the initial configuration of your machine and free access to everything. Once you put the PK in, it's then in user mode, in which case the keys and the boot process are all protected from malicious entries. So this is kind of defines secure boot in the technical details, and how a UEFI defines how that protection is done. It doesn't define what's actually like what policies you might want to have in your protection, like which entities you trust, which ones you don't trust, including how your machine comes configured. Now that's kind of one of the contentious points. So Windows 8 is coming out soon, and as with other versions of Windows, it comes accompanied with a document called the Hardware Certification Requirements. Now, if you want to put a Windows sticker on your Lenovo or your James Corp, who produces laptops, and you want to put a Windows sticker on it for some reason, just to be clarified here, so you're not James Corp, you're someone else, and you want to certify your machines to run Windows. You want to put the sticker on the box so everyone knows it can run Windows. You have to comply with these requirements. And these requirements say a lot of things. There's sorts of stuff about what the platform looks like, what devices are present, how you can boot. Also define that you have to have UEFI support. So every Windows 8 machine you'll see coming out will have to have UEFI support. It also has to have secure boot support. And secure boot has to be configured in a certain way. So they say that the PK has to be present, so it's not in setup mode. They say that this is a public document, by the way, I'm not divulging any secrets here, that there has to be a Microsoft key in the KEC database, there has to be a Microsoft key in the DB database. And importantly, that secure boot is enabled out of the box. So your machine is not going to run malware when you first buy it. It's sort of locked down from the start. Now, there's a process called the WinQual signing program. Now, let's say yes.
So, am I to understand this correctly? You can't actually, you can't buy a Windows machine that's meant. How do people say they want to install Windows? How do they install it on a brand new machine if the PK is already meant to be installed and it can't be in setup mode?
So you've bought a machine and it's certified for Windows 8, or it's not, or
I don't know.
Okay,
I guess that's the essence of my question. Yeah.
Sorry. So buy the bits and build it yourself. That machine probably doesn't meet the Windows 8 certification. So in that case, there's no requirement for secure boot. So you buy a motherboard, there's no requirement for that motherboard to have secure boot enabled. So you're probably going to have it inside mode. It really depends on the motherboard manufacturer, whether they're going to comply with those requirements, even though there's no sticker on it, or what. I'm not a laptop manufacturer, so I don't know how it works. But if your machine is configured is certified for Windows 8, you will have to have Secure Boot enabled and enforced. And I guess the out here is that Windows do have a signing program. So if I want to get my Hello World application installed on everyone's Windows 8 machines, or runnable at least on everyone's Windows 8 machines, I can submit it to this signing program, get it signed by Microsoft, and then it will run on every Windows 8 machine. So there is a WinQual signing program that does that. Now, that's great, but it's not really going to work for Linux, right? So, and talk about our implementation here. Now, the concerns here are that we want you to be able to modify your system. Like we want to explore what you can do with the bootloader. We have to be locked into the bootloaders that Canonical provides. And that's the essence of free software. No one wants to lock anyone into a certain approved binary process at all. Any implementation that we come up with also has to work without having to reconfigure the system, and that's really important as well. We don't want to have to. If you buy a laptop and want to install another operating system on it, and you have to go in through the. Actually, I'll show you what the firmware interface looks like for Secure at the moment. So I've just bought my fancy new Windows 8 laptop. I want to install Ubuntu. Actually, that's not the right one. Okay, let's turn on Secure Boot. If we put in custom mode, load a PK, use a file. I don't have a file present. But we have to load files up into PK. Then we have to do it to KK here, enroll it. We have to provide a GUID in that format. So this isn't easy. No one's going to do this, right? There's at least 3 different keys you have to set. Where?
Once you've generated one PK, can you overwrite it?
Yes, you can. So you can override a PK with a PK signed by that old PK. Yeah, you can update as long as you have the original PK around. Now, this is through the official API. They might BIOS vendors might implement a reset button in BIOS, like in the BIOS configuration screen. So, for example, that method of loading keys, I don't have to sign those keys. I can just load them up and do that sort of thing. But any programmatic access to PK, KK, any of the key databases has to be signed and has to be authorized if you're in user mode, not setup mode. So the reconfiguration here means that we don't want users to have to go through the BIOS screens, load keys, even worse, type in keys, 1K of key data. That's not going to work. And we also wanted to use the infrastructure that Ubuntu has. So we want to make sure that that sort of rules out the WinQual approach. When we build a new bootloader package, we're going to have to submit that to WinQual and get that signed and that sort of thing, and go through those hoops to basically run the software that we want to run that we've written on our own computers the way we want to do it. So these are the kind of the approaches that I think any free software implementer would put on their secure boot implementation. So this is the story. So we have you just bought a Windows machine, comes with the UEFI firmware, has a key installed. Now, companies like Canonical and Red Hat could go around to every manufacturer and get a key of their own installed, but the chances of that reaching 100% of market are not going to happen. There's no way that we will get a Linux key on every single laptop in the world. There's not the market imperative to do it. Some companies just aren't interested in Linux. I don't know why. And we can't guarantee that if you buy a laptop off the shelf that maybe it has the key, maybe it doesn't. That's a kettle of fish that we can't really deal with. And unfortunately, that's the case at the moment. It may change once Ubuntu or Linux in general is picking up, and there is a larger market coming around of people who want Linux on their laptops, and that's kind of growing. But we're not at that stage yet where we can start kind of getting OEMs interested in having our key installed out of the box. So
Well, that's the interface thing that you were talking about before with the software. Will that allow you to do a read of what public keys are in there?
problem is running. How do you run your software on there to read what keys are in there?
No, once the thing's already running.
But how do you start your software?
Sorry?
How do you get your software running?
I assumed that there was software access to the BIOS.
Sure. But how do you run that software?
Without running Windows first.
Or not just how do you run the software?
Running it from Windows.
So you're running like a user's, like a
User space program.
yeah, okay. Yeah, that could definitely read the keys.
So you could use a user space program out of Windows
Yep.
to look at what public keys are available. So if you walked into Harvey Norman's, you could go out of your USB key, stick it in the side and go, okay, what public keys are on there?
Yeah, but I think that's a bit of a burden for my mum to have to do that in front of my computer. Yeah. Let's say I'm away and she wants to
The
vote.
question is always, does that interface, the interface does give you access
Yeah,
to what public keys are there?
Yeah, you can definitely read the keys that are in the system.
Okay.
It's probably we can't kind of do that in the Ubuntu installer CD. We can't sort of check out what keys are in there because you have to be signed by something to start looking at the signed keys. So, yeah. But yeah, you could definitely do that. And there's probably tools already in there that you can use to inspect the UEFI variables and whatnot. You probably like flick through the BIOS configuration to see what's there. But again, depends on the implementer. But their standard interfaces would work. So, like we get this new system has a key installed, at least one key. We know that the Windows certification requirements say that it must have a Microsoft key present, and it's probably certified to run Windows. So we know there's a Microsoft key there. So the first thing that we plan to do is have a boot shim that's gone through that WinCall process. And that is signed by Microsoft. It does very little. It just it starts running, and it also has another public key installed, embedded in that boot shim. Now it uses that public key to verify the actual bootloader. Now the thing here is this key can belong to someone else. It doesn't have to belong to Microsoft. We can have that being an Ubuntu key. And then we can sign this bootloader with the Ubuntu key and sort of basically pass off that authentication from a Microsoft key to an Ubuntu key. So now we can start signing bootloaders with an Ubuntu key and having them verified in exactly the same method, use the same embedding algorithm and the same signing algorithm to start booting that bootloader. And we can still assure that this has been verified. This is actually not malware because it's been signed by an official key that's trusted by this. This has been signed by an official key that's been trusted by this. So we have a chain of trust that goes to the bootloader here. It's just we're not using that same method. We're not having to get our key distributed in every single firmware implementation in the world, which is a great relief. So that.
Wouldn't that also mean that if Microsoft got wind of it, they could just revoke the boot shim?
They could. There would have to be a reason for them to do that, though.
It's Linux.
That's not a good reason.
Yeah. We're talking about Microsoft.
Is it Red Hat that's paying them $100 per machine?
Well, that's
Is
the
that
same.
what they're paying for?
It's not per machine. It's paying them once. Yeah. So that $99 is to join the WinCall program, and paying that is required to sign any number of things.
Oh, once, not per machine.
No.
Oh, okay. All right.
Yeah, not per machine or per signing. It's just a once-off fee. Yeah, $100 per machine. That wouldn't really cut it. Yeah. So we got our bootloader running in our secure environment. The bootloader does what a bootloader does and boots a kernel. Now we've made the distinction here. Before executing a kernel, the bootloader calls exit boot services, and that's where we've drawn our line on where the verification can stop. So we're saying, okay, we're using this signature verification process to protect everything up until that exit boot services call, which means that we can't any malware won't be kind of affecting the UEFI system. From that point onwards, we're running a Linux kernel, and that's run as Linux kernels are today. There's no signing, or there's no driver authentication or anything like that. Now, it's possible that you might want to implement that. That's fine, but our present plans aren't to actually do any signing and verification of the Linux kernel. Other companies are definitely doing so. I think Google possibly signing, or at least using some sort of attestation for their boot. I'm sure other companies are very interested in doing that sort of thing, but we don't want to. We'd rather not have our users having to re-sign everything if they want to change a kernel module. Brings up all sorts of problems for any modules you want to compile yourself and install, things like the NVIDIA binary as well. If that's built every time you install it, that simply can't be done if we're signing kernel modules. So we decided to go for this plan at the moment. In deciding, or in saying that we're going to not lock down, but we're going to have that verification process up until that exit boot services call. After that, we're in our own territory, I guess. Now, yes.
Just going back to the two key stores of DB and DBX.
Yes.
Using this approach, then I'm assuming you're never going to be able to write to DBX, and therefore you're never going to be able to invalidate a key.
Not if we.
But wait, there's more.
Yeah.
Go ahead.
So on some machines, and our plan. So we do some work in pre-installing Ubuntu on various machines, and that's going very well. On machines that we have some say in the certification process, we're going to say put the Ubuntu key into your Kerr database. And that means that we can distribute updates to your DB and DBX databases. If something's compromised, we don't have to rely on Microsoft to start revoking that, to get that key into people's firmware. So that's our plan, and is to have, where possible, have that key in the firmware. We're also having that key publicly available. So if you have installed Ubuntu or Fedora or whatever on your machine, and you want to get updates from us about that, you can put that key in, which will then manually insert the key, which will then make your system upgradable via our key process. So that's the plan, and you can also take it out if you don't want it. So it's optional whether or not you want to have that key present, and whether you want your DB and DBX managed by a third party. Now, importantly, the Windows certification requirements also specify that Secure Boot has to be disableable, and that users must be able to reconfigure or put their Secure Boot configuration into custom mode and put their own keys in and take them out. And that's I think a big win for us in terms of if you want to use your own key, if you don't trust us, that's fine, or don't trust Ubuntu, that's fine. Put your own key, sign your own things, awesome. The only gotcha is that only applies for x86 systems and not ARM. So the Windows certification requirements for ARM systems say that there's no reconfiguration and no disabling Secure Boot. So I think it's unfortunate, but it's quite similar to how things are with some devices today. Some phones, just you can't upgrade, you can't do any reconfiguration. But there's very little we can do there. But less worry about that because of the. It doesn't mean 100% of the machines on the market will be in that configuration. Whereas for x86, if the Windows requirements say so, 100% of the machines in the market are going to be in that configuration. So that's the story there. A couple of links. UEFI.org, that contains the specification for UEFI. This second link on the wiki, that's how to build your own UEFI firmware and get it running in QEMU, as you've seen me do just then. We've recently put our implementation plans, basically a text-based description of that on the Ubuntu Devel mailing list, if you want to get into some gritty details. And this is our signing tool. This is what we use to basically take an RSA key, EFI image, and sign the image. So if you want to start signing your own stuff, you can use that to do so. It's also packaged up in the next version of Ubuntu as well. So that's it. Any questions?
So you're saying this is the current plan for Ubuntu. Is it in place? Like, has that boot shim been signed by with the WinQual program and all that stuff?
It's in progress.
So Microsoft are saying it's going to happen. Because I mean, they just say no, and it kills the plan.
But they have a signing program, right? They allow people to sign software to run in UEFI. I think that would be reasonable and say, sure, you can run Linux. I think there'd be some consequences if they didn't.
Yeah.
I mean, it's a fair marketplace. But yeah, they're not going to do something.
Yeah,
stupid,
they'd have
right?
to be pretty mean. But otherwise, that seems like a nice plan. If you do that, then we don't have to worry about the secure boot thing in new Windows 8 certified hardware.
I think
it should just work.
Well, yeah, that's fine, and getting the right balance between user freedom and having things just work, I think is something we really need to work on, and we've been very careful about trying to get the right balance there. And I think we've come up with something that is acceptable. But yeah, we'll have to see how it goes. And for all plans that are sort of dependent on external entities, we sort of we'll have to see how it goes. So yeah.
Is Apple doing secure boot, and if so, can we still put Ubuntu on Macs?
I have no idea actually. I think most of the sort of the drive behind secure boot is coming from Windows 8. I don't know Apple's internal plans, but we haven't seen any systems using secure boot, and it's all done by Windows 8. So I guess by October we sort of starting to see that happen, but I haven't heard anything from Apple. Yeah.
I've heard Matthew Garrett claim that running an insecure kernel mode stuff would allow you to sort of pretend to be a UEFI implementation and load another operating system and sort of kill the security of these systems.
Yeah.
Is that likely to cause a problem with Ubuntu's chosen solution?
Yeah, it is a difference between our and Fedora's implementations. So Matthew works for Fedora. He's sort of my equivalent in that side of things. He works on the EFI sort of stuff, and we work together quite well. I'm very happy with that. So Fedora's implementation is we basically carry the verification an extra step, actually two extra steps. We verify that the bootloader then verifies the kernel. Kernel also verifies all the modules. Anything you run at kernel mode has to be signed, has to be verified to that extent. So his justification there is that if we don't do this signing step, this could be malware. That malware could then start a pretend UEFI implementation. That pretend implementation could say, yes, I am running a secure boot, but not actually be running a secure boot, and load all sorts of things. Then boot Windows. Now we're sort of down here. So it boots Windows, and then you have Windows running, thinking it's in secure boot mode, but not actually being in secure boot mode. I think my concern about that is, okay, so we've done this. Let's say we've verified the kernel now. We've verified all the modules. We start a virtual machine. Now that virtual machine starts a compromised UEFI, which then starts to compromise Windows, which thinks it isn't compromised because the firmware's telling it the wrong thing. So now we're at the stage where we have to also stop virtual machines from running. And how much of that do we have to protect? So we've drawn the line here. Fedora have drawn it over here. I think both are valid. I think kind of how it rolls out of the next October onwards will dictate which, if one solution isn't acceptable to Microsoft, maybe one of us sees compromise happening to the Fedora or the Ubuntu models. In either case, there'll be some possible change in either of our plans, but we'll see how it goes. Does that answer your question, Joe? Cool.
Any others?
Also read that apparently with Windows 8 there's going to be And this is what I want to ask you: is it on booting up or actually booting up to Windows that basically you have to indemnify Microsoft from?
I have no idea. Sorry.
Yeah, you have to indemnify them and promise never to take class action against them.
So that was the Sony firmware upgrade, wasn't it?
Yeah, I think that's where they got the the idea.
But
from.
yeah,
I
I haven't run Windows for a while, but I
I'm
really
just
can't say,
wondering
yeah.
if it comes, if that, like, comes with the secure.
All I can say is we're not planning to do the
boot.
same thing in Ubuntu.
Yeah, no, but if you are using the secure boot with the PK sign, but I don't know at what point you're actually like signing that EULA, like.
Yeah, I think it'd be
or accepting it.
I don't know if that's anything to do with secure boot as such. I mean,
No, well, I guess my concern is like, if you're booting into Linux, but you're like indemnifying Microsoft, like,
I'm not a lawyer. I don't know how this works. So, yeah, sorry.
I've just had an idea about how I can demonstrate some of the pre-firmware issues in terms of getting keys into the firmware. Do you want me to run through that briefly? Just 2 minutes?
How you can get the keys into that?
This isn't a question. This is me asking if you want me to give a bit of a demo talking about different levels of manufacture. It'll only take 2 or 3 minutes.
Sure, if you like to.
Yeah, I know a bit about...
Let's ask the audience. Are you guys interested?
Audience, anybody not interested in hearing that? All right. Okay, just take the jacket off first.
Can I sit
Anyway,
down?
awesome. I know about a bit about encryption, so I have an idea of how the key signing stuff works. All right. Let's pretend Lottery West make motherboards. They don't, but let's pretend they do for this exercise. They'll stick the flash chips on there, and they'll put a firmware image in there, right? Then the motherboards go to a PC manufacturer, right? So let's pretend this first table here is a big factory that makes PCs using motherboards. And let's say this second table here is a computer shop. They're the people who put all the components in the computer case, stick the Windows 8 certification sticker on it, and boot it out the door. This line, this white line here, which you probably can't pick up on that camera, this is the front door of the computer shop. The machines are not allowed to go out the door without that Windows 8 sticker on them. This is my reading of the regulations that Microsoft have put in place before they will allow people to sell machines with Windows 8 on them. So if you were really lucky, you could speak to the motherboard manufacturer and get, say, for example, the XYZ Linux key put in the firmware in the factory. You probably wouldn't get that because it probably doesn't even leave the factory with a PK on it. So it's still the BIOS with the UEFI firmware would still be in setup mode when it leaves the factory. So I reckon you've got to target either one of these two places, either the people who builds the PCs, like assembles them, or the people who actually sell them, right? So this is the computer shop. Chances are this is where the PK gets put in the machine and it goes from setup mode to user mode. They then install Windows on it, or they might not install Windows on it, but either way, it's got the Windows 8 sticker, it's in user mode, it's got a PK in there. You can't put any additional keys in using software at this stage. You've got to type them in manually, as Jeremy suggested. So yeah, I reckon either speaking to the manufacturer or the computer shop, because either one of these two can put a PK in the firmware, right? And before the PK goes in, you can put in as many keys as you like, and it only has to be sort of signed, sealed, and delivered before it leaves the actual computer shop here. So yeah, you could have a Harvey Norman PK get put in it here at Harvey Norman, and as long as they've signed a Ubuntu Keck key encryption key with their Harvey Norman PK, you can then install, you can boot Windows on it, install a Ubuntu key in there that Harvey Norman have signed because it's in the KEK, then it'll all work. And that's, if you want to lobby manufacturers or computer shops to say, we want to have our Linux distribution's key put in this machine before it leaves the shop, then they may very well agree to it eventually. You won't get all of them, but you might get some of them. And if you join a big group of people and lobby through something like Electronic Frontiers Australia, you've probably got a better chance than you do if you ring up the computer shop yourself. All right. So, yeah, any questions on my micro presentation? Thanks, Jeremy.
And at the same time, Nick, if we've got anything coming in from IRC, obviously it takes a couple of seconds for that to go through, and if anyone's there. Oh, Jason, we've got another one. Hang on.
Well, you can just repeat the question.
No, I'll run to you. I'll run to you. Here we go.
So it's a bit simple for that. We don't have to. There's no. There's not necessarily a restriction on putting keys in before PK. There's only a restriction on doing that automatically. So yeah, it's possible to do the manual process at any stage, including after that. Yeah. Well, yeah, it is laborious, but it's kind of the simplest thing. I mean, you probably won't have to type in the keys manually. That's sort of worst case scenario, but it's at the moment I have a little script that I use with my firmware images that just loads in all the types in the right data, navigates the menus, and sort of puts the key in. So it's automatable, but it's you definitely have to be present as a user in front of the machine to prevent any sort of automated attacks that don't have someone standing there putting the key. So sorry, yes.
Well, something that maybe I missed or we didn't ask is I can understand SecureBoot has to be enabled to meet the Windows certification requirements, but can you just disable it? I know that you don't want your mum to have to boot into the BIOS setup mode to stable it, but is that an option? Yeah,
definitely. And
on x86.
On x86, and I mean you can do that. We also lose the security that SecureBoots get you. We don't want to be a second-class citizen in the security world either. We don't want to say Linux is less secure than Windows because they don't support SecureBoot.
Sure, yeah, in business that's probably more important than me running my Ubuntu.
But why shouldn't you be entitled to the same security that their other machines get, right? So,
but it's another out.
It's also a, you can't claim this is restricting too much because you can just disable it. So yeah, it's kind of a balance, right? So yes.
How does this affect PixieBoot environments?
Anything Pixie booted also has to be signed. Any image that is executed has to be signed before it's run, and that includes things like option ROMs. So, if anyone's unaware, you have some PCI cards have a bit of ROM on them, which contain code that needs to be run at BIOS time. So, classic example is video cards, which contain a small amount of VGA BIOS on them. When the machine's knitting, the BIOS jumps into that, starts running it. That also has to be signed. So any kind of any code, any instructions that want to be run on a machine have to be signed in a SecureBoot environment. So, yeah. Yes.
Jeremy, one more. Free Software Foundation have criticised Canonical's approach, mainly because they're dropping Grub, because they're concerned that the GPL will force them to have to publicise their keys.
Mm-hmm.
Do you have any comments on that? I know it's not official Canonical.
Yeah, again, definitely not. This is all my own point of view. I'm not speaking for Canonical here. But the issue is this bootloader here probably won't be Grub, because Grub is released on GBV3. Some interpretations of the GBV3 say that if you ship something that's signed, if I'm shipping something that's GBV3, I have to give you facility to build exactly that same image, and that may require the keys to do so. Now, the general exception to that is if I can reconfigure this firmware, you can run whatever you like, really. So you can build your own Grub, you can put your own key in, you can have exactly the same functionalities you had before. Now, the concerns that Canonical have expressed is what if someone ships this firmware with a not quite working reconfiguration system, so you can't actually do that? Then what's the remedy for that situation, and what's the do we have to does Canonical have to disclose the keys for that bootloader now? And that's a pretty dire situation. If keys have to be disclosed, then anyone can sign bootloader those keys, and those keys will likely be revoked very quickly. And if you think about it, so if a Linux distribution has their keys revoked, that's kind of it's a big thing, and so it means that all the CDs people have, all the images, will no longer work on any machine that has that revocation in place, and that's obviously not a good thing. So that's something that should be, we need to work out what we can do to not have that key revocation happening. And I think I read on Mark Shuttleworth's blog, the main argument is that there's no assurance that won't have to happen. So the FSF statement, I think the wording was, we can't think of any situation in which the keys have to be disclosed, but that's not a very strong statement. So the worry here is that under some clauses of GPLv3, those keys may have to be disclosed. I'm not a lawyer, so I can't say how likely that is or it isn't, but it's something that needs to be thought about. Now, not saying this is going to be a closed source bootloader. It's EFI Linux. I think it's under the BSD license at the moment. Source is available. Source for the signing tools is all available. So it's trivial to rebuild that same thing. It's not going to be a closed source component of the system. It's just the plans for a GPLv3 bootloader aren't there. That's all.
Is it only the sticker that makes you put the encrypted UEFI on it? Like, you can boot Windows 8 onto the bare metal without the UEFI on it? The reason I'm asking is, if it is a problem, then has anybody looked at doing virtual machines and bodging the UEFI through the virtual machine so you can boot the Windows image?
What's the problem you're trying to solve there, though?
If the Windows 8 requires the UEFI on it.
Yeah. So what's the scenario? I have a laptop. Do I have a...
Yeah, will it boot on uncertified machines?
Yeah, I don't know what...
Well, I don't know if it is or not. Or is it only coming out on new machines? I don't know.
Yeah.
That's logical, but we're talking Microsoft here.
Yeah, they're a sensible company. They probably want to, capture that market as well. So I don't see why not. Yeah.
How did Microsoft get to be in this position of?
I think you're asking the wrong guy here.
Yeah, because if you, as you say, it's all spearheaded by Intel. How did Microsoft end up writing most, like large parts of the specification, and like being in charge of,
specification
most of the keys?
Isn't the problem. I mean, the specification defines, like I said, the mechanism, not the policy. And it's like saying someone's using GPG to, I don't know, for some nefarious purposes. It's not GPG that's actually provided the problem there. It's the usage of it that's, it's the restrictions that are enforced by the technology, not the technology itself. So I'll say that so UEFI has a number of organizations behind it. It's not just Intel, not just Microsoft. But Windows, like Microsoft, is quite free to say what requirements you must meet to get the sticker and get that official endorsement. So that's not an issue. But
they did end up writing quite a bit of the specification as well, I thought.
Well, it's a working group, so there's contributors from all over the place. But I guess the fundamental thing here is that market share. That if the reason why 100% of machines are going to come shipped in that configuration is because 100% of machines are going to be shipped with, not 100%, but a large amount of machines are going to be shipped compatible with Windows 8. So that's the rub, I guess.
Any other questions? Any more? Okay, please thank Jeremy for his talk.
Thank you all.